Okay, we'll try again. Lots of technical problems. Yes, the screen's moving finally. Okay, I gave you this type of question here, talking about efficiency and energy, because we already talked about the equation where we talked about eta and eta's value, and we expressed it in terms of velocity ratio, and we said eta was equal to MAVA, remember, mechanical advantage over velocity ratio. And we've done the derivation of that equation in class, and we got to that particular equation by looking at the actual definition, which is energy out over energy in. So I've done this type of question just to remind you that although that is the equation that you can quite often use for lots of your questions, you still got to remember that essentially eta, efficiency, which equals efficiency, is equal to energy out of the system over the energy in. Now, in a perfect system with 100% efficiency, they are equal to each other. So we get 100% or 1, and when you multiply it by 100, you get 100%. So energy out over energy in, if they're both equal, you get a value of 1. But we know that this system doesn't give us a value of 1. We know, if for this we're talking about calculate the output, we know that our efficiency is 85%, and we can express that as a decimal. So we can say that 0.85, which is eta, our efficiency, is equal to the energy out, which is what we're trying to actually work out. I'm going to say E out over the energy in, and we've already said the energy into the system is 4,000 joules. So then we just multiply the both sides by 4,000 to get the 4,000 away, this pesky 4,000 on the bottom, and we end up with 0.85 times the energy in is equal to the energy out, and that's equal to, I'm going to write it here, energy out is going to be equal to 3,400, and what do we measure our energy in? Of course, we measure it in joules. And that is the answer for that question. So we've got two equations for eta, the efficiency. Now we've got MA over VR, and of course energy out over energy in. Okay, so just remember those two equations, because they will come in very handy at some point in time in your life, maybe next year in the HSC. Okay, if here we've got a question about an effort arm. If the effort arm of a class 1 ideal lever moves at 20 meters per second and the load arm moves at 10 meters per second, what is the mechanical advantage of this lever? Well, first of all, you've got to see that they've said an ideal lever, so we know that it's 100% efficiency. So with 100% efficiency, we can say MA is equal to VR. Okay, the mechanical advantage is equal to the velocity ratio. Now, for the first two questions we did with the pulleys, we couldn't make that assumption because they weren't ideal systems, because there was friction in the system, and we didn't have 100% efficiency. But because they've said it's ideal, we know that we've got 100% efficiency. So for this type of question, velocity ratio is exactly what, so I'm going to write here, VR equals velocity ratio, and that's the ratio of the velocity, okay, meters per second, and MA is mechanical advantage. Okay, so velocity ratio is just a ratio of the two speeds. Okay, so in this case, it's equal to effort arm velocity over the load arm velocity. And when you think about it, if there's a mechanical advantage that's allowing you to lift something, the effort arm, because it's further away from the fulcrum, it has to travel faster to move the load arm a shorter distance. Okay, so it's kind of like if that's your load and this is your effort. Okay, because this is further out. Okay, for this load to move that very short distance here in the same time, okay, instead of having to move that distance, it has to move this distance, which is a lot bigger. So in the same time, it has to cover a bigger distance. So effort is going faster, okay, in this instance, if there's a mechanical advantage that's greater than 1. So we've got here the 20 meters per second is the effort arm. So all we have to do is put the two speeds over the top of each other. You say 20 meters per second over 10 meters per second, and that equals 2. So we can say MA equals 2, and that's your answer. Okay, so that's just showing you that you know, you can work out mechanical advantage as effort arm over load arm, or you can work it out as force of the load over force of the effort. And there's lots of ways of doing this. Okay, so this is just one more way of thinking about things. So that is your question 7. For the final question, question 8, the answer is actually going to be, we worked it out, it's actually going to be B. Okay, now so a lot of people said A. They said, because they were looking for the biggest mechanical advantage, and they go, well, that looks a long way, and that looks a short way, so that's got to be the best one. Okay, so that you can always come unstuck when you're playing around with this type of question. What you needed to do was go through each one and work out the mechanical advantage for each one, counting. In this instance, look at effort distance over load distance. Okay, effort arm over load arm. So we can say MA equals distance of effort over distance of load. Okay, so effort distance over load distance. So for this one here we go 1, 2, 3. Okay, so the load distance is 3. And if we go this way, we go 1, 2, 3, 4, 5, 6. Okay, so effort arm is 6, so that should be on the bottom. So 6 over 3 equals 2. So this A has a mechanical advantage of 2. And so a lot of people said that A was the answer. Well, let's calculate B, because B is the correct answer. And we'll do exactly the same thing. We'll work out the effort arm distance, 1, 2, 3. So MA, our effort arm is 3, and our load arm is only 1. So 3 over 1 equals 3. So this actually has a mechanical advantage of 3. Okay, that's the easiest one, the one that will take the least amount of effort. Okay, because it has the greatest mechanical advantage. So that is why you need to test the answers. Don't just look at think that's the easiest one. Anyway, hopefully that's helped you out. Let me know if you've got any questions about that, and I'll see you in class.